Hi and welcome back to DMAD Marine Mammal Research Association's free QGIS lessons. I'm Tim Aubrey and today we're going to begin to look at raster data, which is a topic that I know a few of you are really interested in. The lesson is a little longer than some of the others and I was considering splitting it into parts just so it's a bit more bite-sized, but it's only about 20 minutes long, so I'm sure you can just pause it halfway through if it's too much, if you don't have enough time. But yeah, get stuck in. Okay, so I'm sure a couple of you have heard of raster data before and may even be aware of a couple of its uses, but raster data is actually a really wide-ranging topic and there's a lot more that we can do with it than a lot of people think. So today we're just going to discuss what raster data is, we're going to understand when it can be useful, and we're going to understand what the different types are and some of the issues with raster data. Okay, so far we've used vector data, and that is the points, lines and polygons, and we've used these to represent real features. Raster data aims to capture the world in a slightly different way. In raster data we have a grid of pixels, or a grid of cells, and that's made up of rows going down our screen and columns going across our screen, just like an Excel spreadsheet, and then one of these rows and column squares is called a pixel. So the vector data we've used is really good for certain things, and you'll remember in one of the first lectures we showed you this map of Montenegro, and this map's made up of lines and polygons, and these are great for representing discrete features such as the roads, the rivers and the lakes. So these are discrete characteristics, and that means they've got a very obvious defined outline. We know where the edge of our road is because it goes from black tarmac to green grass, for example. So where is this vector data not as useful? Well, vector data is not as useful for what we call continuous data. And continuous data can be things like colours. So the example I've got here is the colour of trees, which can be an indicator of tree health and general vegetation health. So we could make polygons for several different colours, so we could go for maybe a dark green and a lighter green, but in order to make the different coloured polygons for each different tree shade, we'd literally have to have thousands if not millions of polygons, which just wouldn't be particularly convenient, and there'd be massive file sizes. So this is where raster data is really useful, and many people use raster data as a backdrop for their vector data, and actually the work we've used with Google Satellite is technically an example of this. So we had our vector data on the front, so we had our and then we had our raster data, so the satellite data, or even the open map data we've used is also raster data because it's a picture in essence. However, we don't just have to use this for satellite and for photos. We can use raster data for a couple more abstract ideas, such as illustrating weather. So we can look at how weather patterns change, such as rain, snow, wind, that sort of thing. And I'm sure you've seen the weather patterns on the television after the news, and that's raster data. So the image created there is raster data. So in order to use this raster data, because as I said they're pictures, we actually have to tell our GIS environment, so in this case we'll be telling QGIS where our data is. And this is a process which is referred to as georeferencing. And when we're georeferencing, often our pictures or aerial images have certain information. So our grid of cells is likely to have the top left coordinate, which I've indicated with a star, and then the pixel dimensions, so the X and Y, and then if any it might have information about the rotation as well. However, not all of our data has this information, and it's also possible to match key points known as reference points. We normally want to have an absolute minimum of 4 or 5 reference points, and these can be things like, it really depends what scale you're working on at this point, but these can be things like very defined corners of buildings and things like that, which we can match on our topographic map to our satellite map or aerial photo or whatever it is we're using. If we're at a much bigger scale, then we might be looking at matching entire cities to entire cities, for example. And this is particularly useful when we're using older maps or scanned maps, which obviously weren't around when we started this geoprocessing sort of phase. So very old maps which were around before the birth of GIS can still be really useful because they can show us what used to be there. So we can look at how maybe a city's expanded or how a river might have changed its course, for example. So we've got 2 key types of raster data. The first is remote sensing, and that's what we've talked about so far, and that's the stuff from the planes and the aerial vehicles. And then we have compiled data. So our remote sense data is probably the more likely type of data, just because we have so much background mapping and things, and this involves images captured from satellites and also aerial vehicles. This used to mainly be done by planes, but now I'm sure you've noticed it's quite common to capture these sorts of images with drones, so with the unmanned aerial vehicles. And they can also be captured by things like balloons and stuff like that. And remote sensing doesn't just have to include our standard red, green and blue that we get in a normal camera. It can also include things like infrared, and this is really common when we're checking on the health of crops in farming. So this is stuff which is outside of our natural vision. Compiled data, on the other hand, is data when we get it from multiple data points, and we use these points, or very occasionally lines, to make a raster data file in a process known as interpolation. So the classic example are weather stations. So I already talked to you, if we've got lots of different weather stations, then we can begin to predict rainfall, and we can begin to predict wind and things between these weather stations. So that's the classic example, but this could be more abstract. So we can have things like crime statistics, we could have things like accidents or wildfires, and we could mark where these events happen and interpolate them to look at where we might also be likely to have things in the future, or where things might have been likely to occur in the past but not reported. Okay, so the next thing we're going to talk about is the phenomena which is spatial resolution. And in spatial resolution, each pixel has a size, and this pixel size, so the X and Y value, is what determines the spatial resolution of our data. So you may have noticed that as you zoom in on, say, something like Google Satellite, it eventually gets to a blurry level. I mean, Google Satellite is actually a phenomenal resource, and it's got quite an incredible coverage of the planet. So this is just a random area of Colombo in Sri Lanka, and you can see that when we're looking at it in terms of towns and lakes, and we've got a railway there, then actually it's really quite crisp. And then as we zoom in further, the edges become more and more blurry. So you can see that the house we have here, the roof is looking quite out of focus, And that's actually because that edge is made up of lots of different pixels, and that's what gives it the blur. You may have noticed on the map on the left that Google Maps actually uses vector data combined with its satellite data. So the roads we have here that are marked and the railway are marked as polylines. So that just keeps it clear, because you remember that polylines don't change as we zoom in. They just redraw as we zoom in, so that they never lose their focus. And some satellites are capable of capturing imagery with cells which are sort of on the meter level, so generally around 10 meters. But aerial photography now, we can get down to tens of centimeters, and potentially even less with drones, because that's sort of unlimited depending on the flight height and things like that. Okay, so that's when we're looking at our remotely sensed data. When we're using compiled raster data, like the weather data, then our resolution will be dependent on the density of our information. So if we've got lots of points, then our data is going to be more dense, and our resolution is going to be better. And if we have more sparse data, then our resolution is obviously going to be worse. So we've talked about spatial resolution, but there's another phenomenon we need to be aware of, which is called spectoral resolution. And we often have a number of different bands in an image. So I've used the example of RGB, and RGB is red, green, blue values. And this is how a camera captures its images. So each of those is a color band. So we look at the reflection of red, green, and blue light, and each of these bands are put together. And the number of bands that we have is referred to as the spectoral resolution. So when we're just working with one band, then this is known as grayscale. So this is where our image goes from black to white, and you often see this with elevation data, for example. Our darkest areas will be the lowest lying areas, going up to the highest areas, which will be white. And often we can use pseudo color. So pseudo color is where we change these black and white values to represent other values. So we might have something that runs from red through yellow to blue, or vice versa, to make these images easier to understand. And remember that we have these other sensors as well, which are outside of our visible spectrum. So I've already mentioned infrared, but there's others as well. And these are known as multispectral images. So when we have our classic RGB values, and then we have infrared as well, it means we can view the actual color of the crops, and then we can look at these infrared values as well to look at the health of the crop, for example. And this is just known as multispectral images. It can be useful to switch between raster, vector, and raster data. So as a very basic example, we vectorized some of our building data, road data, and tree data from the satellite data. So that was actually turning a raster into a vector. But the computer can also automate this in some cases. So, for example, say we had a raster which was elevation, and we wanted to know all the areas that are above 1,000 meters. We can use tools in GIS environments in order to automate these. So we're left with polygons, which are all the areas that are above 1,000 meters. It can also be really useful to rasterize vector data. So this is where we're taking our vector data, and then we might use the interpolation to make a raster. So like I said, with the weather stations, but say we did this with precipitation, then that would mean that we'd lose all the other data that we had for that weather station. So we would lose the information. If we did it about precipitation, then we'd lose the information about wind, for example. So raster analysis. We've already talked a little bit, but we can use raster analysis in a great number of ways. I've just listed a couple of examples, and these are things like modelling water flow on land. So if we know the elevation, then we can begin to model where water's likely to go, where we might have catchment areas, etc., etc. And this can be really useful for flood modelling. We can also look at disaster management. So using quickly, if we use satellite imagery, we can look at the spread, and we can look at what factors might cause that spread once we know where it's gone. So for example, the extent of fires. And finally, we can look at agriculture, as I've mentioned several different times. So what do we need to be aware of when we're using raster data? Well, I've already mentioned it, but we just need to really be aware that there's a possibility that we're going to lose some of our data. If we convert from vector to raster, we should always make sure that we keep our original file so we don't lose any of the data associated with each of our vector points. And that's just because the raster data doesn't have the same attribute table that our point data does. The second is that these images that are massive data files. So if you consider that our data files are taken by satellite, and we could zoom into virtually every house on the planet using Google Satellite, that's obviously a massive amount of data. So they're very high resolution photos, and they often cover a huge area, and so we need to be able to have a computer which is able to sort of hold all this data. So just final slide is a bit of a summary slide, just going through what we've learned again. So our raster data are a grid of regularly sized pixels. So we saw that grid image at the start. They're really good for showing continuous data, but they're not quite as good for showing vector data. Discrete data, and that's where we should use vector data. Our spatial resolution is defined by the size of our pixels. The smaller the pixels, the higher our spatial resolution, but therefore also the higher the file sizes. Spectoral resolution is defined by the number of bands. So do we just have one black and white band, or do we have RGB values, or do we have multispectral values? And you'll remember that these multispectral values are the ones that occur outside of our visible spectrum. The single band images that we can have are called grayscale, and these can be shown in pseudo color by the GIS. So you remember I talked about the idea of elevation and coloring our elevation values from black and white so that they represent something which is much easier for us to interpret. And finally, we just need to be aware that when we're using raster images, these can consume a large amount of storage space, so we really need to think about what it is we need. Okay, that's it for today. Thank you.